Okay everyone, we're going to do a video here on how to do the problems on this vectors and relative motion worksheet. So we'll just go through them one by one. You can skip ahead if you want or watch it 1.5 or double speed, whatever makes it easy for you. First of all, when we're talking about things in one dimension, then we want to make sure if they're going in the same direction, you add them together. If they're going in the opposite direction, you're going to subtract. Pretty simple. So for this one, you're riding a train with a friend. The train's moving at 40 meters per second. So I'd just like to draw an arrow for my 40 meters per second like that. Be nice if my arrow were a little more straight. And then find the overall velocity of the ball if you throw the ball forward on the train. So train's going that way. I throw the ball forward at 15 meters per second, and then I want to find the overall velocity of the ball. So I just have to add them together like that. Oops. And that's 40 plus 15. So that would be 55 meters per second. And I would say forward, since I asked for a direction right there. You have to give the direction. What if you throw the ball backward? Okay, well, we're going to draw some arrows again. So there's my 40. I'm going to drop the units just to make things look a little bit nicer. And then I'm going to draw this back at 15 that way. So I'm going to subtract them this time, and my overall result is going to be 40 minus 15. So that's going to give me 25, and it's still going to be forward. So I kind of running out of space here, but hopefully maybe if you did this on a separate sheet of paper, you're going to give yourself enough space. So for the airplane one, it's really the same problem. If I have my 400 mile per hour airplane and my 100 mile per hour tailwind, I'm just going to add them together to get 500. And then, of course, if it has a headwind, I'm going to take 400 this way, I'm going to take 100 this way, and subtract them, and I'm going to get 300 overall. There we go. Okay. Moving right along, it's the same thing. One dimension's pretty basic. There's really not too much to it, except if you kind of get to the problem 4 when you're going back and forth and back and forth. But if I'm going 20 meters per second through the river, and the river's flowing 15 meters per second relative to the land, if the boat's moving upstream, so upstream means it's going against the current, so that means I need to make them going the opposite direction. Probably make that one a little bit longer to make it 15. And then my overall result here is going to be 5. And once again, I'm dropping my units, but I should really have units here, meters per second. And then if the boat moves downstream, then I'm getting 20, and I'm getting 15. So my overall is going to be 35. Cool. All right, moving along. Here is this trickier problem. Now I might try to find myself another piece of paper to work this one out on, because I might run out of space here. So hopefully you all can see that one. Maybe I need a little bit more space. So here we go, just so I can draw my arrows pretty big. So you got a train moving down the tracks at 40 meters per second. So that's going to be my forward direction, 40. A waiter pushes a cart down the aisle of the restaurant going forward on the train, 4 meters per second. So I'm going to add in another 4 that way because it's going forward on the train up here. On the cart is a mouse that's moving 2 meters per second toward the waiter. So usually the waiter's at the back here. So that's going to subtract out 2 going this way. On the mouse is an ant that's moving 1 meter per second toward the tail of the mouse. So the tail of the mouse is going to be this way because the mouse is going in this direction. So the tail of the mouse is going this way. So I'm going to add another 1 going that way. And on the ant is a flea that's moving 0.5 meters per second toward the head of the ant. So the head of the ant is going this way, so I'm going to add in a 0.5. So all the ones that are going this way toward the right, I'm going to add, and then the ones that are going this way towards the left, I'm going to subtract. So what's going towards the right? I get 40, I get 4, I get 1, and I get 0.05. And then this one here is the only one that's going towards the left, according to what I see here. Minus 2. That's 44, 45, 45 and a half, minus 2, 43 and a half. So mine is 43.5 meters per second. You can tell me if you see me in class or something, if you got something different or if I made a mistake. But That's what I'm sticking with for now. All right, moving on to 2 dimensions. So we're mostly going to deal with situations where the vectors are at right angles to each other, and you can use Pythagorean theorem. So, I kind of liked it that I had separate pieces of paper to do this. So wait for me for a minute. Okay, so separate pieces of paper, it's just nice to have some extra space here. So we have this number 5, the airplane is flying 400 miles per hour through the air. So I'm just going to draw my 400 miles per hour, just like that. And then find the speed relative to the ground if it has a crosswind of 100 miles per hour. So I'm going to draw a crosswind 100 this way. You could have also done it like this. Either way, the crosswind is good. Now I just have to find the hypotenuse of this thing right here. And the way I'm going to do that is I'm going to do 400 squared plus 100 squared, and then take the square root of it. So we got our handy dandy calculator. I do 400 and I square it, which on this calculator is there, and I add in 100 and I square that. And let's equal all that together. Then I'm going to square root, which is here, and I'm going to square root the answer, which is there, and I get 412.3, but we'll just call it 412. So the length of this one is 412. And if I want to put my units back on here, it's all miles per hour in this problem, miles per hour. Now notice I just said the speed, I don't need to include a direction. My direction could be, well, I didn't really say which way the crosswind was going. So the crosswind could have been going this way or this way. I mean, the original plane could have been going this way or this way or this way, right? So I didn't really say anything. You could find that angle if you wanted to using some trig, but not necessary for this problem. Okay, Joe takes a walk from his house. He walks 100 meters north. Let's make some space here. Good, so I'm just going to start out with Joe walking 100 meters north. There's 100 like that. And then 50 meters west, so I'll just draw it in there. 50 meters west, then 75 meters south. 75 south, things are probably not to scale here. And then 150 east. 150 east. And I do want the displacement, and technically it has a direction, so I don't necessarily need an angle here. But what I can reason is that let's just look in the up and down direction. So in the up and down direction, I went 100 north and 75 south. So if I'm going to draw sort of an overall vector that represents the result of all that, I just had 175, so this is going to be 25 north. In the side-to-side direction, I went 50 west and 150 east. The overall result of those two is going to be 100 this way, 100 that way. So my resultant, that's the result of these things added together, is going to be this one. And then I need to do 25 squared plus 100 squared square root. 25 squared plus 100 squared equals square root that one, and I get 103 for over here. So this one is 103, and it's meters this time. So what we're getting the sense of is that sometimes your answer, your units are going to be meters, sometimes they're going to be meters per second, sometimes they're going to be miles per hour, right? Because vectors can represent displacement, they can represent velocity, they can represent acceleration, force, so your units are going to change just kind of depending on the problem. Okay, let's look at number 7. Motorboat moves at 20 meters per second through a river. The river's flowing 20 meters per second relative to the land. Find the speed of the boat relative to land if the boat moves across the river at a 90-degree angle. So I think I'm going to draw the river, since it's blue, I'll draw the river like this. And the river is flowing at 10 meters per second. And then I'm going to draw my boat going across the river. Oh, sorry, 10 meters per second. The boat's going to be moving at 20 meters per second. So the boat's moving like this, 20 meters per second. Now what's helpful for vectors, it's helpful to redraw them in a tip-to-tail fashion. Because if I draw them like this, it's hard to see exactly how they're adding together, right? But if I redraw them in another spot and I draw them tip-to-tail, then it doesn't matter which one you do first. So I'm going to start with my 10 meters per second for the river, and then I'm going to add on 20 meters per second for the boat, and then I'm trying to find this one right here by hypotenuse. And I said the speed, so the direction doesn't really matter. So there's the river, there's the boat, and then there's the overall. And how I get that one, once again, is 10 squared plus 20 squared, and then square root that. I think I'll just do it all in one line here. So I do the square root of 10 squared plus 20 squared. And hopefully that works, maybe end the parentheses. Okay, cool. 22.4 is what is this going to be. 22.4 meters per second. So there we go. Okay, moving right along. There's the interactive right here, so hopefully you can just play around with the interactive. What I can do is say for this question 9 right here, change the riverboat speed to 10 and the heading to 45 degrees north of east. So on the picture up here, it's going to be like this, and then this is going to be 10. Now find the river speed that gets the boat directly across the river. So how do I figure out what the river speed is? Well, what I need to know, if I'm going to go directly across the river, here's the clue for this going directly across the river. What I need to do is I need to match the speed of the river here, which is kind of in this up and down direction, and I need to match that with the upward component of my boat, right? So whatever this upward component of my boat is needs to match this downward component of the river, and then that's going to get me straight across the river, right? So this is 10. Find the river speed that gets the boat directly across the river. How do I do that? Well, if this is 10 right here and this is a 45-degree angle, let's draw it out a little bit bigger. So there's my boat speed, and that's 10 meters per second. And then this is a 45-degree angle, like that. I need to match this to the river speed. It doesn't really matter what the boat's doing side to side. All that really matters is what is the boat doing in the up and down direction. So how do I figure out this one? Well, this 45, 45, 90 triangle, whatever this side is the same as this side, and then this side is x root 2. Or another way to think about it is, I'll do it in orange. Whatever this side is, if this is x, let's make it a different number. If this is a, then this side over here is a divided by the square root of 2. And then this is a divided by the square root of 2. So if I want to find out what this side is, if I know this side is 10, this side is 10 divided by the square root of 2. So my river speed needs to be 10 divided by the square root of 2. Now your math teachers are going to throw a hissy if you leave it like this, so it's probably better to write this as 5 times the square root of 2. But I don't care if you divide by a square root. I don't know why that's a thing in a math class. Why can't you divide by a square root? So they don't like the square roots in the denominator for some weird reason. Or at least some math teachers that I've met. Okay, so that's that for that problem. And talking about components right here, so this is exactly what I was saying. You can figure out the answer to number 9 if you don't have the simulation by forcing the upward component of the velocity to be whatever it's going to be. Oh, so I should find out numerically what the 5 times the square root of 2 is. 5 times square root 2. 7.07, if you want that in a decimal form. That is, I'll just call it 7.1, and that's going to be meters per second. So on the vector simulation thing, what I can do is I can just set up the same triangle, and I make this 10, which turned out to be 9.9 on the simulation, and I make the angle 45 degrees, and then I can just read off what the y component is right there, 7, right? So I know the y component is 7, and that's 7, and that's going to match my whatever my river speed needs to be downstream, exactly what my boat's speed is upstream in order for the boat to go straight across the river. So once again, this upward component of the boat will cancel out with the downward component of the river, and all you're left with is going straight across the river. So if you have a simulation, it's really easy to do. You don't have to set up this triangle at all. You just, well, you do, but you know the calculations are done for you. Just make it 45 degrees, make this length of 10, which is close enough, and then you'll get the answer right over here. Okie doke. So how do we do this one over here? So you don't have the river simulation, but you can use the PHET simulation to help you out, and I'll kind of walk you through how it's going to go over on this side. Let's see, get myself some space here. Okay, so the boat's crossing the river and needs to get directly to the other side. The speed of the boat is always 15 meters per second, and the speed of the river is 12 meters per second. Find out the angle the boat needs to take in order to get across the river. Okay, so I'm just going to draw the river speed going down this way as 12. And I know that the boat speed, what should we do? The boat is pink. Okay, cool. Is that visible for you all? Let me get a separate piece of paper here because I think it's kind of bleeding through. Let's try this again. Okay. So once again, I'm going to draw the river speed as going down at 12. And I know the boat is kind of going off this way at 15. So how do I get the boat directly to go across the river? Well, what I'm saying, have been saying, is the speed of the river has to match the upward component of the boat. So I know the upward component of the boat has to be 12 meters per second. I guess I'm writing my units on these. Meters per second and meters per second. I know that those two things have to match each other and cancel out. So I need a triangle that has 15 on the hypotenuse and 12 on the opposite side. And I just happen to know the ratios of these numbers because I set it up on purpose as a 3, 4, 5 right triangle. Let me just remind you about 3, 4, 5 right triangles. They look like this. If this side is 3, and this side is 4, and this side is going to be 5. Oh, I did this the wrong way for this problem up here. If this is 3 and this is 4, then this side's going to be 5. Well, you might be like, hey, that's not 4 and 5, that's 12 and 15. I know, but 12 is just 4 times 3, and 15 is 4 times 3. So this one over here is going to be 3 times 3 is going to be 9, which is kind of irrelevant. Oh, actually, it's not. What's the x component of the boat speed as it goes across the river? So it's 9. Now, how could you have done this on the simulation? On the PHET simulation, you could have just drawn yourself a vector. It takes a little while to get, but you would have drawn yourself a vector that had a length of 15 and had an upward component. So this AY over here would have been 12. So you'd have just had to play around with it, play around with it, play around with it until you got it just right. And this would be 15 and this would be 12. And then magically, this would appear to be 9 over on this side. And then the angle for those, if you play around in the simulation, the angle is going to tell you that this is going to be a 53-degree angle right there. So that angle right here is, in these 3, 4, 5 triangles, is 53 degrees. And this side is 37 degrees. I guess I didn't really draw my triangle to the right proportions over there. So play around with the simulation is a good way to do it. You could also do sine and cosine if you wanted to, but it's not totally necessary to do sine and cosine or tangent or whatever it is you want to do. So you can play around with this simulation, because the riverboat simulation won't let you get to these speeds, but you can play around with this PHET simulation and you can figure it out over there. Okay, so that's that. And let's see, should we do this last problem? I guess we should just finish it up. So Jose needs to get to the store from his house. He knows the store is 50 meters in a direction that's 30 degrees north of east. So I'm just going to start out with that one. He needs to go 50 meters this way, and it's 30 degrees north of east. He could walk straight there, but he turns out Jose can only walk exactly north or exactly east. So Jose can walk east and then north. Or he could have gone north and then east, but for some reason we like to draw our triangles this way. So draw Jose's 50-meter walk as a vector, break that vector into components in the north and east direction. That's exactly what I did. There's the north component, there's the east component, and label the north and east vectors with numbers. So I need to figure out what's the magnitude of this and what's the magnitude of this. So this is a 30, 60, 90 triangle, which means the lengths are x, 2x, and x times the square root of 3. So that means if this side is 2x, this side is x, so that means this side has to be 25, and I'll put units on it, meters, and this side has to be 25 times the square root of 3 meters. So we'll be working with these triangles a bunch, and I just need you to get, if you're really quick to do this, that's fine. If it takes you a lot of thought to get from here to there or back and forth, that's great. We just need to practice and get you into the rhythm of doing 30, 60, 90 triangles. So that's it for that one, 25. So the idea here is instead of walking 50 meters at this 30-degree angle, you could walk 25 root 3 meters this way and 25 meters this way, and you'd get to the same spot. All right. Kind of a lengthy video, but hopefully that's helpful, and I'll see you soon.